Welcome to the session. Today we are going to discuss second module question bank. In that second module is relations, functions and lattices. In this question bank, we are going to concentrate on the descriptive answers. Let us first, we are going to discuss what is a relation. What is a relation? See here, the relation A and B are any two sets. A relation from A to B is a subset of Cartesian product of A cross B. A cross B. That means A cross B, let us say, I am having, let us say, A is equals to 1, 2 and B is equals to AB. Then A cross B, we are going to get the Cartesian product of these two. So ordered pairs are 1A and next to 1B and next to 2A, next to 2B. So now this is the Cartesian product of A cross B. Now we are going to consider A if I am going to take 1 to B if I am going to take like this. And we are going to consider a subset of A cross B. So whatever the subset, let us say 1 comma A is one relation, is a one relation. Or I am taking 1A, 1B is again another relation. If I am taking another, let us say 2 comma A is again another relation. So like that the given set itself is also a relation, Okay. So now suppose R is a relation from A to B, then R is a ordered pairs A comma B. R is ordered pairs of A comma B. Suppose I am taking R is like this. So it is having the ordered pairs A comma B, which is of the form. The first value, ordered pairs in that first number belongs to set A and the second number belongs to set B. So 1 belongs to set A and A belongs to set B. A belongs to set B. So for every ordered pair can be written as A related B, A related B. Here what I am writing, 1 related to A. Then I am going to write 1 related to B. Then 2 related to A, 2 related to A. So this way we are going to say whenever A comma B belongs to R, then we are saying that that element, first element is related to second element. Whereas if I am considering 2 does not related to B. 2 does not related to B because 2 comma B is not there in R. 2 comma B is not there in R. So A is not related to B. A is not related to B. So here R is a binary relation from A to B. Since the elements of R are ordered pairs, if we use the term a relation on its own, then it is a binary relation. So here we are going to recall, let us say the Cartesian product of A, B, it is going to be denoted as A cross B, and which is consisting all ordered pairs whose first element belongs to A and second element belongs to B. Now let us go for, we are going to discuss with one example. Let us have A is this and B is this and A class B is this. So 1 to 2 and next 1 to 4. Next 2 to 2 and 2 relates 4. Next 5 relates 5 and 5 relates 4. Like that. We are going to write 5, 2 and 2 to 2 and 2 to 1 to 2. So now let us go, sir. We are going to write one relation. What is the relation? Is the relationship between the numbers as x is less than or less than y. Then we are going to select the ordered pairs in such a way that first element is less than the second element. So R I am taking it as first element is less than the second element. 1 comma 2, 1 comma 4, and this I am not going to consider. And first element is less than the second element, I am going to consider 2, 4. And next another one is 5, 2 I am not going to consider. 5, 4 I am not going to consider. So this is R. This is R. And of course, R is a relation from the set itself. So then we can say that R is a relation from A. So here we are going to say that the relation, simply here relation is between from A to B. Relation is between from A to B. Suppose if a relation is defined on the set A itself, then we are going to write R is a relation from A to A. Or we can say that relation R is defined on the set A. Defined on the set A. Then the another one is, what are the union and intersection of a relation, then complement of a relation, then converse of a relation. Converse of a relation. That we have to discuss. Now, what is a relation? What is a relation? So here, a relation, let us say, R, we are going to consider R and S are two relations. R and S are two relations from A to B. From A to B. Then the union of, see here, R is a relation from A to B and S is a relation from A to B. Then the union of these two relations defined as R union S, R union S, which is defined as set of all ordered pairs A, B such that A belongs to A belongs to A, and B belongs to B belongs to B. That means the first element belongs to set A1 and second element belongs to set 2, and another one is A, B belongs to R, A, B belongs to S. Belongs to S. Okay. So here R and S are two relations from A to B. Then the union operation, if you are going to perform, so that is denoted as R union S, and it is defined as A, B such that A belongs to A, B belongs to B, A, B, ordered pair A, B belongs to R, A, B belongs to S. So this is nothing but the union operation of R and S relations. Then now we are going to get the intersection. Intersection of two relations, R and S, denoted as R intersection S, and it is defined as A, B such that A belongs to A, B belongs to B, and A, B belongs to R, and A, B belongs to S. A, B belongs to S. So both are belongs to R as well as belongs to S. So that is known as a intersection. Then we are going to know what is the complement of a relation. Suppose R is a relation defined from A to B means complement of R, we are going to define it as R bar. So then complement of R, we are going to take it as R bar is defined as set of all ordered pairs A, B such that A, B belongs to R, does not belongs to R, but it is belongs to A cross B, and A, B does not belongs to R. So in this way we are going to define this. Suppose we are going to say that A is equals to one set. Let us say 1, 2, 3. And B is another set. Let us say 3, 4, 5. Then we are going to define R as, let us, I am going to take it as 1, 3, then 1, 4, then 3, 3. Let us say I am taking like this R. And next another one is S, and S is the another relation, and we are going to define it as 2, 3, then 2, 4, then 3, 3, then 2, 5. 2, 5. These are the two relations. Then I am going to find out what is R union S. Let us say first R union S. So R union S is nothing but set of all ordered pairs which are belonging to R as well as S. So this is nothing but 1, 3, 1, 4, next 2, 3, 2, 4, then 2, 5, then 3, 3, 3, 3. This is R union S. And what about R intersection S? So the common ordered pair is nothing but 3, 3, 3, 3. So this is R intersection. Now, what about R complement? R complement. So set of all ordered pairs which are not in R, but it is there in A cross B. But it is there in A cross B. See here, 1, 3. So A cross B is having 1, 3, 1, 4, 1, 5. So I am going to, 1, 3 is there in R. So I am going to consider 1, 4, 1, 5. Then the another one is R bar. Next 1, 4 is also there. So this is also we are not going to consider. R, 4, this is also there. So we are going to get only 1, 5, 1, 5. Then the another one is 2, 3. 2, 3 is not there. So we have to consider 2, 4 is not there. Then we have to consider. Then 2, 5 also there. And next 3, 3 is there. We are not going to consider. 3, 4 and 3, 5. 3, 4 and 3, 5. So this is a R bar. This is known as a complement of a relation. Complement of a relation. Now another one is the converse or inverse or inverse. So what is the converse or inverse of that is nothing but R be a relation from A to B. Then the converse or inverse we are going to represent like this. A R inverse or R converse. R converse. R inverse, that is nothing but R is from A to B. Then the converse is from B to A. B to A. So for that we are going to write R inverse as, let us say, for every A comma B such that and B comma A belongs to R inverse. Belongs to R inverse. Belongs to R inverse, and whereas A belongs to A and B belongs to B. B belongs to B. This we are going to represent as R inverse. R inverse. So in this way, let us say I am going to consider for this R is given, and what is R inverse is equals to, then we are going to take it as 3, 1, 4, 1 and 3, 3. 3, 3. So this is nothing but a converse of a relation. Converse of a relation. So these are the operations which are going to perform on the relations. And now we are going to discuss what are the properties of a relation. So first one is a reflexive property. So what is a reflexive? A relation R is said to be reflexive. R is said to be reflexive if for every A belongs to A, for every A belongs to A, then A comma A belongs to R. A comma A belongs to R, then that relation is known as a reflective. That relation is known as a reflexive. Suppose if I am going to take A is equals to 1, 2, then R is a relation defined on the set A itself. So which is consisting, let us say I am taking 1, 1, 1, 2. 1, 1, 1, 2. So here for every element of A, that is 1 belongs to A, 1, 1 is belongs to R, whereas 2 if I am considering 2, 2 does not belongs to R. 2, 2 does not belongs to R. So that means 2 belongs to A, then 2 comma 2 does not belong to R, so R is not reflexive. R is not reflexive. R is not reflexive. So that is the way that we are going to find out for each and every element of A belongs to A, then AA does not belong to R, then it is known as a reflexive. It is known as a reflexive relation. Then the another one is, so here let us say 1, 2, 3, 4, R is we are going to consider a relation like this. So here 4 comma 4 does not belong to, so it is not reflexive. It is not reflexive. Then irreflexive means A comma A, for every element A comma A does not belong to A. Does not belong to A. Then it is known as irreflexive. That means no element of A is repeated by itself. Is repeated as is related to itself by R. No element of A is related to itself by R, then it is irreflexive. Suppose if I am considering less than relation, greater than relation, or nothing but a irreflexive defined on the set of real numbers. Whereas if you are going to say that greater than or equal to, less than or equal to, then automatically then it is nothing but a reflexive we are going to get. And here irreflexive, less than or greater than are nothing but the irreflective relations. Suppose if I am going to consider a relation is like this, defined on the set 1, 2, 3, then 1, 1 is there, 1, 1 is there, but 2, 2 is not there, 3, 3 is not there, then we can say that it is not irreflexive. It is not irreflexive because 1, 1 is there. Because 1, 1 is there. So this relation is not irreflexive and not reflexive. So it is both. That means whenever we can say that if it is not reflexive, does not means that it is irreflexive. So a relation which is not reflexive and which is not irreflexive also exists. So here for this, here we are going to say that this is not reflexive because 2, 2 and 3, 3 does not, and the same way it is not irreflexive because 1, 1 belongs to R. 1, 1 belongs to R. Then another one is symmetric. Symmetric means whenever A comma B belongs to R and B comma A belongs to, whenever for every A comma B belongs to R, then B comma A belongs to R, then we can say that that relation is symmetric. Suppose A comma B does not belongs to R, then there is no necessity for saying that B comma A. Suppose if I am taking a relation defined on the set A equal to 1 to 3, relation I am taking it as 1, 1, 2, 2 and 3, 3. Let us say I am taking a relation of this form. And here A related B element is not there. There is no question of B related A. So in such a case, this is automatically asymmetric. So whenever A comma B belongs to R will be there, A is related to B is there, then we go for B related A. Then B related A is there, then it is a symmetric. If A is not related to B, then there is no question of B related A. B related A. In such a case, it is automatically asymmetric. Now, symmetric relation. So, and a relation which is not symmetric, then is called asymmetric relation. Asymmetric, we are calling it as a asymmetric relation. Suppose if I am taking A equal to 1 to 3, then here 1, 2, 2, 1 is there, and these two are not symmetric, then R1, see here, R1 is 1, 2 is there and 2, 1 is there. So, it is a symmetric relation. Whereas here 1, 2 is there, 2, 1 is there. But 1, 3 is there, there is no 3, 1. There is no 3, 1. So, R2 is not symmetric. Then it is only asymmetric. And next, antisymmetric. A relation R on set A is said to be antisymmetric. If whenever A, B belongs to R, then B comma A belongs to R. That means whenever they are A related B is there, B related A, then if they are equal, then we can say that it is a antisymmetric. Then the relation is known as a antisymmetric. Suppose less than or equal to any relation will be there. A is less than or equal to B, B is less than or equal to A, then both should be there in R. Then we go for verify whether A equal to B or not. A equal to B or not. So in such a case, we say that it is whenever they are equal, then we can say that it is antisymmetric relation. Otherwise, it is not antisymmetric relation. Suppose A is given and R1, R2 are two relations defined on set A. Then we are going to verify whether R1 is antisymmetric or not. So R1 is 1, 1 and 2, 2 will be there. And see here A related B is not there. So we can say that it is asymmetric. It is asymmetric. Then we can say that it is also we can call it as antisymmetric. So there is no A related B, there is no B related A, then there is no question of A equal to B or not. So here A related B is there and B related A is there, then 1 is not equal to 2. 1 is not equal to 2. So R2 is not antisymmetric. R2 is not antisymmetric. Then the transitive relation. A relation R on a set A is said to be transitive. Say is said to be transitive. Whenever A comma B belongs to R, B comma C belongs to R, then AC belongs to R, then we can say that it is a transitive. It is a transitive. The ordered pair A comma B belongs to R and B comma C belongs to R, then A comma C belongs to R, then we can say that it is a transitive. In the same way, A comma B belongs to their R, but there is no B comma C, then need not worry about A comma C related, A is related to C or not. So in such a case, automatically it is understood that it is a transitive. It is a transitive only. So here, A less than or equal to B, B less than or equal to C, less than or equal to are the relations, relation defined between the set of real numbers. So then we go for A related C. A related C, which is a transitive. Suppose greater than or equals to another relation, greater than or equals to another relation defined on the set of real numbers. So A is greater than or equals to B, B is greater than or equals to C, then we go for A is greater than or equals to C. Suppose if I am going to take the relations are like this, it is given, the relations are like this, R1 and R2. See here, 1 to 2 will be there, 2 to 3 will be there, then 1 to 3 is also there. And 3, 1 will be there, 1 to 3 will be there, 3, 2 also there, 3, 2 also there. So then we can say that it is a transitive. But whereas in the R2, 2 to 3 will be there, 3, 1 will be there, 3 is related to 1, 1 is related to 3, then 1 is related, 1 to 3, 3 to 1, then there is no 1, 1. There is no 1 is 1, 1 does not belongs to R2. Does not belongs to R2. Then we can say that it is not a transitive. It is not a transitive. Suppose if I am not having this, okay, this if I am going to remove 1 related to 1 related 2 related to 3, then obviously 1 related to 3, it is also a transitive. It is also transitive. Suppose if I am going to keep like this, then 1 related to 3, 3 related 1, there is no 1 related 1. So we can say that R2 is not transitive. R2 is not transitive. And another one is the compatibility relation. The compatibility relation. A relation is said to be compatible if the relation is reflexive as well as it is symmetric, then we can say that it is a compatibility relation. Compatibility relation. So here A is equals to this set and R is a relation defined on the set A. Now we are going to verify whether it is a compatibility relation or not. So for that we have to verify a reflexiveness first. So reflexiveness means 1 will be there, then we go for 1, 1. It is there. 2 will be there, then we go for 2, 2. 3 will be there, we go for 3, 3. 4 will be there and we go for 4, 4. 5 will be there, then we go for 5, 5. So it is reflexive. And next, the symmetric, for every A related B, 2, 3 will be there, then 3, 2 will be there. 2, 4 will be there, then 4, 2, 4 will be there, then 4 2 will be there. 2 5 will be there, then 5 2 will be there. So every A related B will be there, then there is a B related A, then there is a B related A. So it is a asymmetric, it is a symmetric. Hence we can say that the relation is satisfying. So both the reflexive as well as the symmetric, then we can say that the relation is a compatible relation. The relation is a compatible relation. Now, let us, we are going to discuss another concept. See, every relation need not be a function. Every relation need not be a function. But every function is a relation. Every function is a relation. So here, whatever in the relation, let us say 1, 2, 3, A is consisting 1, 2, 3 and B is consisting A, B, C. A, B, C. So we are going to take it as 1, 2, 3. See here 1 is related to A as well as 1 is mapped to B. Then this is simply a relation. It is not a function. It is not a function. See here unique element will be mapped only a unique element in B. Or if I am going to take, there are one or two elements, one or more elements are mapped to one element which is there in B. So here I am going to take it as, let us say if I am going to consider this is a function. This is a function. And here R is, I am going to say that 1A and 2A and 3B. So this relation is a function. This relation is a function. So, and whenever the relation, if I am going to take like this is not a function. This is not a function. So that's why we are saying that all relations are not function, but every function is a relation. Every function is a relation. Now we are going to discuss the different types of functions, and we are going to discuss in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.